Hello and welcome to lesson 9. So in the previous lesson we looked at logic gates, quite an interesting lesson. I enjoy that. Now this is quite the challenge. So counting systems 1. So part 1 of a 2-part lesson, looking at counting systems that computers routinely use. Now we've got 4 main counting systems. We've got binary, otherwise called base 2, octal, sometimes called base 8, decimal or denary, sometimes called base 10, and hexadecimal, sometimes called base 16. Okay, and here we can see a range of numbers. So first of all, what I'd like you to do, maybe pause the video before I give you the answers. Try to match the counting system with the range of numbers you think that they use. Okay, so if you want to pause the video now, while you do that, and then you can unpause, you can resume the video when you think you have an answer. Okay. Right, okay, so welcome back. So base 2, so 0 and 1, so 2 distinct values, yes? 0 and 1, base 2. Octal, base 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 distinct values here. So this is the range of numbers for octal. Denary or decimal should be nice and straightforward for us all. 0 to 9. And hexadecimal, 0 through F inclusive. So 16 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 distinct values there. So these are 4 important counting systems, and we're going to try to get better acquainted with them in this lesson and in the next lesson as well. So, right, so we've got binary, octal, decimal, and hexadecimal. Okay, I'd like you to try to complete these. Let me turn off these non-printable characters, it's a bit distracting. I'd like you to try to complete this table as best you can, using these numbers here and using what's in here. Can we complete this table? Okay, so take as long as you need, pause the video and resume the video when you are ready to check with me. Okay. Right. Okay, so we'll do this together. So let's do the easy ones first. Okay, so 0, 0, 7. That's a decimal, 8, 9, 10. Okay, right. Well, decimal is done for us. Okay, well that's no fun, is it? So let's try and do hexadecimal. So 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, so that's quite straightforward, I think. Yeah. Right, that's the easy 2 done. Decimal and hexadecimal, quite straightforward. Now, binary. So 0, this is 1, this is 3. So how is this 3? So if this is 1 and this is 3, how do we make 2? So 2 probably looks like this. So 0, 1, 2, 3, we can call this 3. 4, right, so what does 4 look like? So if this is 3 and this is 5, and this is 1, then 4 must be that. Let me make this red. 6. Right, okay, so this is 5 and this is 7, so 6 must be 0, 1, 1, 0. Must be logical, yeah? This is 5, this is 7. So we can infer, we can understand that this digit here means 4. We know that this digit here means 1. We know that we can have a very strong guess that this digit here means 2. So this is 6. So decimal 8, well, we can see 7. and we can see 9. So decimal 8 must look like this. Decimal 9 looks like that, decimal 11 looks like that, so decimal 10 must be that. Because we know how to make 2, and we know how to make 8, so we know how to make 10. Decimal 12, well, if we look at 11, and if we look at 13, decimal 12 probably something like that. So that probably means 8, so 8, and then this means 4, so 8 plus 4 gives us decimal 12. 14, right, okay, so we've got binary 13, we've got binary 15, so probably looks something like that. 8 plus 4 plus 2. 8 plus 2 is 10, plus 4 is 14. Super. Super. Right. Octal. 0, 1, 2, 3, 4, 5, 6, 7. 7. After 7, what number comes after 7? 10 comes after 7 in octal, because there's no number 9. So we loop round. We have our most significant 1, and then 0. 12, 13, and 16. Right, and this is key. Yeah? So we've got a decimal here, 0 through 15, hexadecimal, 0 through F, octal, 0 through 17, and binary 0000 all the way through to 1111. Right, so far so good. Now, because computers use binary base 2, we work to the power of 2 a great deal. So 2 to the power of 0 has a value of 1. 2 to the power of 1 has a value of 2. 2 to the power of 3 has a value of 8. And so on and so on. So what I'd like you to do now, again, maybe pause the video. Can you complete these tables? You'll need to use Google or a calculator to help you. Can you complete these tables? Pause the video and resume when you think you have something. Right, okay. So welcome back. So 1, 2, 4, 8, 16, 32, 60, 32, 64, 128. So 2 to the power 7 is 128. Over here. And then down here. Yes, so 2 to the power 8 is 256, 512. So it doubles each time. Yeah, so 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 81, 92, 16,364, 32,768. 2 to the power 16 is a very important number in computing, 65,536. 2 to the power 32, also a very significant number. 4,290,000, hang on, no, this is billion. 4,294,967,296. 2 to the power 64 is, so that's thousands, hundreds of thousands, millions, billions. That's a huge. That's a very big number. 2 to the power 128 is a huge number, and 2 to the power 56 and 2 to the power 512 are stupidly huge numbers. But these numbers are important. Do any of these numbers look familiar to us? Well, they should. We probably have either 8 gigabytes of RAM, or maybe 16 gigabytes, or maybe 32 gigabytes of RAM. We don't have 30 gigabytes of RAM. Never. We never have 20 gigabytes of RAM. Never. Our hard disk might be 512 gigabytes. Might be 1024 gigabytes. So a terabyte might be 2048 gigabytes. Yes. We never have hard drives that are 600 gigabytes doesn't work. 2 to the power doesn't work. Yeah. So these numbers should start to look familiar to us. Yeah. If we look at our computer, this computer here, storage, 250. Yeah, he's probably hiding the truth a little bit. It's probably 256 with 5 gigabytes reserved for some system partition. Yes, but I'm sure the hard disk space there is 200. Actually, is 256 gigabytes. In terms of RAM, can I have a look at that? Storage, display. Yes, a level 2 cache, yes, a 256. Memory, 4 gigabytes. Where else are we likely to see? Yeah, so 2 gigabytes. So we've got 2 banks of memory, so each one is 2 gigabytes, making a total of 4 gigabytes. No PCI slots. Storage. Capacity, 250 gigabytes. Maybe there's a hidden partition somewhere. 250 gigabytes is not a reasonable number. It should be 256. So there's probably some hidden system partition somewhere. Right, so these numbers should start to ring some bells with us. Now, so we're going to look at these numbers. We're going to look at how to work with these numbers between each counting system, which is not something that's very trivial to do. Not very trivial at all. So we're going to have to pay attention here. So let's look at these numbers. So we've got number 127, 128. These are decimal numbers. So 127 decimal, 128 in decimal, in 8-bit binary. Okay, so 8 bits make 1 byte. Yeah. So this least significant bit here has a value of 1. This is 2 to the power 0, so this has a value of 1. The second least most significant bit has a value of 2. This has a value of 4. This has a value of 8, value of 16, value of 32, value of 64, and a value of 128. So if we want to represent 128 in 8-bit binary, it looks like this. It looks 1, 0, 0, 0, 0, 0, 0, 0. Because we have 1, 128. We have no 64s, no 32s, no 16s, no 8s, no 4s, no 2s, no 1s. So if we add all of these together, where we have a 1, 128 plus nothing, plus nothing, plus nothing, plus nothing, plus nothing, plus nothing, plus nothing is 128. 127. Okay, so we have 1, 1, we have 1, 2, 1, 4, we have 1, 8, we have 1, 16, we have 1, 32, we have 1, 64. And if we add all of these together, if we add 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, then we get the number 127, which is 1 less than 128, which is shown here. So, how to write 66? Yeah, that's the question. All right, so have a go at that. Pause the video, and you can resume when you think you have something. Right, okay, so 66. No, I think this is quite straightforward, actually. So we have 1, here, we have 0 here. We have 0 here, just for completeness. And then we have 2. So here, here, put zeros in here, and that's 66, yes? So 64 plus 2 is 66. So 0, 1, 0, 0, 0, 0, 1, 0, 66. Easy enough, yeah? I think so. Right, okay, now, write these numbers, or try to write these numbers in binary. Okay, so these are all decimal numbers. Can you write these in binary? Again, pause the video and you can resume when you're ready to check with me. Okay, so 166. So we've got 128 plus 32 plus 4 plus 2 gives us 166. The next one, 213. 128 plus 64 plus 16 plus 4 plus 1 gives us 213. 111, 64 plus 32 plus 8 plus 4 plus 2 plus 1. 42, 32 plus 8 plus 2. 250, 128 plus 64 plus 32 plus 16 plus 8 plus 2 gives us 215. 7. 4 plus 2 plus 1. 7. 199. 128 plus 64 plus 4 plus 2 plus 1 gives us 199. And the last one, 177. 128 plus 32 plus 8 plus 2 plus 1 gives us 171. Right, okay, so hopefully that was fairly straightforward. I mean, there's nothing very, very difficult about that. Yes, once we understand the concept, quite easy. Right, okay, so what's the maximum number that we can represent with 8 bits? Well, we need to have a look here. Yeah, so if all of these are 1, so if we make that a 1, so what's the maximum number that we can represent with 8 bits? If we add up all of these, we know it's going to be an odd number because we've got 1 here. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So the maximum number, I think, is 255. So our range for an 8-bit number, an 8-bit byte, is 0. 0 is the minimum when everything is 0, and 1 is the maximum. And when everything is 1, 256, I think, is the maximum. Right, okay, so can we convert these 8-bit binary numbers into denary? Okay, so now we're going backwards. Yeah, so here we had the denary, we had the decimal, and we had to figure out the binary. Now we're doing the opposite. Okay, so can we convert these 8-bit binary numbers into denary? Denary just means decimal. Yeah. Okay, again, pause the video, and when you're ready to resume, press resume. Right, okay, so 1 1 1 1 0 0 1 1 0 0. So we add 128, we add 64, we add 8, we add 4, and we get denary 204. 241, 167, 85, 24, 173, 93, and 219, I think. So we've attempted to work with binary and decimal. We've looked at some examples of how we can represent decimal numbers in binary and how we can work with binary numbers, converting them back to decimal. So that's 8-bit binary numbers. 8-bit, remember, is 1 byte. Yeah? So 1 byte on modern day computers consists of 8 bits. But what about 16-bit numbers? Yeah, so 16-bit, 2 bytes. Then it's the same. It's just a bit longer. It just takes a bit more time. Just the numbers are just a bit bigger. Yeah. So 1, 2, 4, 8, 16, 32, 64, 128. Much like in this table up here. Yeah, much like in this table here. 1, 2, 4, 8, 16, 32, so on. 128, 256, 512, 1024, 2048, 4096, da 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 da. So to represent 1000, we have 512 plus 126 plus 128 plus 64 plus 32 plus 8 gives us denary 1000. Denary 10,000, 8192 plus 1024 plus 512 plus 516 plus 16 gives us decimal 10,000. Okay, so if we want to represent decimal 10,000 in 16-bit binary, this is what it looks like. Yeah. Okay, so what's the minimum? Well, let's come back to that. Let's do this exercise first. Yeah, so here we've got some 16-bit binary numbers. Can you work out the decimal? Yeah, so put these in here. So this is the first 8 bytes, this is the second 8 bytes, so put those along here, and then add them up, and we should get the decimal answer. Pause the video, and you can resume when you want to check together. Right, okay, so let's look at this first one. Do I have my answers hidden? Oh, super. So 110, 1100, 1100, 110, 110, 111, 00, 11100. Okay, comes out, if we add all of these up, comes out as decimal 52,444. It's just a case of adding 32,768 plus 16,384 plus 2048 plus 1024 plus 128 plus 64 plus 16 plus 8 plus 4 gives us the decimal answer. And here I think are the other answers. So 52, 465, 42,764, 21,979, 6,145, and 44,542. Again, nothing really groundbreaking about this. Nothing super difficult. We put the numbers in and we just methodically add them up, and then we get the decimal answers. Right. Well, hopefully so far so good. Now, this is going to be a challenge. So we've got some numbers here, yeah? Well, we've got some questions here. Use the table above. Okay, maybe that's not clear. So I mean this table. I mean this table here. Yeah? I mean these two tables. Use these tables to try to convert between these different counting systems. Okay, now this is not very straightforward at all. So right, okay. Well, this is not very straightforward at all. So let's work through these together. Yeah. So we'll work through this half together, and this half you will attempt to do by yourself. Yeah. So let me shift things around just a touch. Okay, let's leave that there. this here. What was I doing? So we're going to work through these questions together, and then the other side of the page you're going to attempt to do yourself using the same principles. Okay, so the questions that we're going to work through: binary to decimal, octal to decimal, octal to decimal, decimal to binary, and so on and so on. The numbers are different, but the principle is the same. Yeah? So what's 0, 1, 0, 1, 0, 1 in decimal? Well, this is nice and straightforward. Yeah, so that's 1 plus 4, 8, 16. So 16, 16, 8, 16 plus 4 is 20. So that's nice and easy. That's 21. Yeah. Now, what's 22 in octal in decimal? 22 octal in decimal. Right, so we need to go back here. So 2 so octal 2 is this 0, 0, 1, 0. Now, because it's so 0, 1, 0, 0. Now, because it's octal, we don't need this fourth bit. Yes, octal, the maximum number we can have in octal is 7. Yes, which is 111. Yeah, so we only need 3 bits to represent the maximum value in octal. We only need 3 bits. So 2 in octal. Hang on, let me double check this. 0, 0, 1, 0. 0, 0, 1, 0. Yeah, so this is 2 in octal, of course it is. Now we don't need the fourth, we don't need the most significant bit. So this is 2 in octal. So copy this because 22. Yeah, so 2 and 2. So if we put this together, 0, 1, 0, 0, 1, 0. Yes, then we've got the binary. And now we just convert this binary to decimal. So 1, 2, 4, 8, 16. So 16 plus 2 equals 18. So what is 22 octal in decimal? 22 octal in decimal is 18. What is 22 decimal in binary? 22 decimal in binary? Oh, okay. So we know that this is 21, and that's 1, and that's 2. So if we make that and that, then we can be confident that that is 22 in binary. Let's double check. So that's 1. So 2, 4. So 6, 8 plus 16. So 16 plus 6 is 22. So 22 hexadecimal in octal. Allah. 22 hexadecimal. So 2 in hexadecimal, 0, 0, 1, 0. 0, 0, 1, 0. Yeah, so 2 in hexadecimal is 0, 0, 1, 0. 2, 0, 0, 1, 0. So this is 2 in hexadecimal, this is 2 in hexadecimal. So 0, 0, 1, 0, 0, 0, 1, 0. Okay, now how to convert this to octal? Well, octal, we understand, works with just 3 bits. So we need to split these into 3s. Let me just check my notes here. So 0, 1, 0, we know it's 2. 1, 2, 4. 42. So 22 hexadecimal in octal. 22 hexadecimal. 22 hexadecimal in octal is 42. Very good. Now, 345 octal in binary. 345 octal in binary. Good Lord. Right, so 3 in octal, 0, 0, 1, 1. So 3, 0, 0, 1, 1. 4 in octal, 0, 1, 0, 0. And 5 in octal, 0, 1, 0, 1. Okay, so 3, 4, and 5. What is it? 345 in octal. 3, 4, 5 in octal. Now, of course, because this is octal, we don't need the most significant bit. So 3, this is 3, this is 4, and this is 5. And then, if we put all of these together, hopefully, 345 in octal, we don't need the most significant bit. There we go. Yeah. So let's run through that again. 0, 1, 1, 1, 0, 0, 1, 0, 1. And just to double check. There we go. Yes, so 345 in binary. So we 345 octal in binary. This is 3 in octal. This is 4 in octal. This is 5 in octal. We just concatenate them all together. And there we go. That's the answer. So 345 hexadecimal. Right, well, I think we can reuse these. Now hexadecimal, of course we need the 4th bit. And then we have, so 345 hexadecimal in decimal. So we don't need these. We don't need these leading zeros. Or do we? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So 345 hexadecimal. So 3 in hexadecimal, 4 in hexadecimal, and 5 in hexadecimal. Yeah. And then we just concatenate these numbers together. Now, so this is the binary. Yeah. So it's useful to go via binary. And this number, if we convert this into decimal, we can see 837. 837. We could do the maths, adding 1 plus 4, 8, 1632, plus 64, 128, 256, 512. So if we added all of those ones together, I'm sure we would get 830, 837. Right, okay, and the last one. So what is 110000 binary in octal? So 111 is 7 in octal, and 000 is 0 in octal. So I think the answer is 70. There we go. Very good. Right, okay, so we've worked through these examples together. We've attempted, let's say, to work through these examples together. What I'd like you to do now for the rest of the lesson is to work through these answers together, work through these answers using the same methodology. Put the answers in here, and at the start of the next lesson we will check those answers together. Okay. Right, so a lot to take in this lesson. Counting systems are difficult, but they are very, very important. It's why we're spending 2 lessons on them. Next lesson we looked at signed and unsigned. Before we can look at signed and unsigned, it is important that we try to better understand what we've attempted to cover in this lesson. Okay. All right, guys. Very good. See you in the next lesson.